Welcome to another episode of the Businesstalk podcast. I'm Deepak, your host for today's episode from India. We are honored to welcome Dr. Laurie Heller, Professor of Psychology in the Department of Psychology at the Dietrich College of Humanities and Social Sciences at Carnegie Mellon University, as our distinguished guest for today's episode. Dr. Heller is a leading expert in cognitive neuroscience, cognitive science, and perception. Her work focuses on how people use sound to interpret events in their environment, uncovering the acoustic cues that support sound recognition and exploring how this knowledge shapes both perception and brain activity. Her research spans multimodal perception, including the integration of hearing and vision, the influence of sound on human gestures, and how listeners learn to use echoes to understand surrounding spaces. She also investigates sound categories, the impact of unwanted sounds, and develops collaborative applications to support hearing impaired listeners and improve machine learning systems for sound event classification, with potential benefits for auditory displays, hearing aids, and navigating tools for visually impaired individuals. Dr. Heller holds an SB in Brain and Cognitive Sciences from MIT, a PhD in Psychology from the University of Pennsylvania, and completed a postdoctoral fellowship in the Neuroscience program at the University of Connecticut Health Center. At Carnegie Mellon, she teaches courses on auditory perception, research methods in cognitive psychology, music cognition research, and perception for both undergraduate and graduate students. She is actively involved in several interdisciplinary initiatives, serving as affiliated faculty with the Carnegie Mellon Neuroscience Institute, CMU Music and Technology, the CMU Center for Transformational Play, the CMU Slave Lab Security and Privacy Institute, and the Center for the Neural Basis of Cognition. Beyond campus, she contributes to the broader research community as chair of the Auditory Perception and Cognition Society and as an associate editor for the Journal of Acoustical Society of America. Today, Dr. Laurie Heller joins us to explore her groundbreaking research from echoes to AI, translating human sound perception into technology, and how insights from human listening are reshaping intelligent audio systems. Let's not keep you waiting. Please join me in welcoming Dr. Laurie Heller to the podcast. Dr. Heller, we are deeply appreciate your gracious acceptance of our invitation. It's an honor and privilege to have you with us today.
Thank you for that introduction, Deepak.
Professor, your research on teaching naive listeners to extract information from echoes is fascinating. Can you walk us through how the human brain learns to interpret these acoustic signals? And what does this tell us about our innate capacity for echolocation compared to animals like bats?
So echolocation is a really interesting domain for understanding human plasticity because we aren't supposed to echolocate, but we can see what it looks like for animals that do. So what humans normally do with echoes is we suppress them. When we're processing information, we usually take the first wavefront that comes to us and really process the direction of that wavefront to decide where the source of the sound is coming from. And that's a very important function of hearing. Where is the source coming from? Everything else that comes after that is an echo that's delayed because sound has taken time to travel from, say, the speaker's mouth, for example, over to a wall and then bounce off it, and then a copy of that sound comes to us a few milliseconds later. So if we were listening to that, we'd be confused. We would think the person was coming from all over, right? So normally we are listening to that first wavefront and we're localizing it, and everything that comes later, the echoes, they tell us about the room we're in, how far away the walls are, how spacious the room is. You can tell from echoes whether you're in a house of worship that's large or a small studio that's, and that's what echoes are normally telling us. Now, echolocation is a case where you have to unlearn that way of processing the echoes, that is suppressing them for localization and just using them for spatialization sense. We have to suppress or undo that suppression and learn to actually pay attention to the location and the information in those later echoes. And in particular, pay attention to the time delay between when that first sound comes and its copies that come later. because that time delay is crucial for telling us how far away an object is. If we emit the sound, like make a click, or in some animals they'll make a little chirp, but if we make that sound and then it bounces off of the object that we're interested in hearing, then, or knowing about, let's say sensing, then the amount of time it takes for the acoustic waveform to reach that object and bounce back to us, it's a matter of milliseconds, and that's information about how far away it is. So the first thing echolocation tells us is how far away is this thing, and that's not normally what we do with it. And the other thing it can do is tell us like the angles if you get more advanced, and also it can tell you how large the object is and so on with more advanced echolocation. But just starting with that basic thing, there's something in front of me and this is how far away it is. We taught people to do this who were young adults who'd never tried this before. We gave them a pre-test, then we gave them 15 hours of training with just learning this kind of a cue, and then we gave them the post-test. Some people actually picked up sensitivity in the post-test to actually echolocating, where they would make a click and know with their blindfold on that there was a board in front of them, a big board. And that's pretty cool, but some people didn't pick it up. So 15 hours isn't necessarily enough for everyone. So it shows that there's individual differences, but the existence proof is that there is plasticity, that people who've never tried to do this before can do it. So that's a really interesting case. There's also research that other people have done in other labs where they've looked at the neural basis for this and shown how the neural structures change as blind people either have done it since birth. If they're blind since birth, some people have been echolocating to navigate since childhood. Many people spontaneously have found that. And then also some people in later adulthood who become blind are maybe trying to train. And that was where the impetus for this research came from, is could someone later in life learn to use those echoes? So those are what the cues are, and our capacity is not as good as bats, but some adults who have been doing it their whole lives are very impressively good.
Professor, what are the primary acoustic cues that allow us to determine where a sound is coming from in three-dimensional space? And how do these cues differ when sounds come from above, below, or directly besides us?
So the primary acoustic cues are the differences between our ears in the acoustics that arrive. So that if a sound comes from my right, it's louder in my right ear because my head shadows that acoustics, less of it energy gets to my left ear. If it comes to my right, it also hits my right ear just microseconds before it hits the left ear, like less than a millisecond. And that time difference is also it. So we have interaural level differences and interaural time differences. Those are the primary cues that we use to tell how far something is left to right. And then you asked, how do these cues differ if it's coming from above or below? Well, then we don't really have that as a primary cue. So then we have to use actually our pinna, and the fact that our pinna are shaping the frequency content of the sound. And because our pinna aren't exactly the same above and below, there are ways in which the sound is funneled into our ear canal differently already just from the start, from the shaping of our pinna. So we use the pinna and also our head to shape the sound to know whether it's, say, above or below us, or behind us, or in front of us. So we have other cues like that. And those are called the HR, head-related transfer function, or HRTF. You'll see those they're on a lot of products already right now.
Professor, how are your discoveries about sound perception informing the design of more effective hearing aids and auditory assistive devices?
So I'm not directly working for any hearing aid companies. I'm doing basic research that can be used by the hearing aid companies if they wish. It's public domain. But the design of hearing aids has historically focused on the perception of speech and prioritizing those frequency regions that support speech and the acoustic cues that support speech, which is absolutely appropriate. But my focus is on environmental sounds. Environmental sounds are also a safety issue for people with hearing loss. You need to hear certainly a fire alarm, but a knock on the door, whether the sink is running, whether a baby's crying, and so on. So um, the hearing assistive devices, if they're focused purely on enhancing speech, may not be optimized for certain kinds of environmental sounds that have different acoustic structures. So that's where my research has focused, has been on how hearing impaired listeners hear the causes of the sounds around them for environmental sounds, and how that may differ if it's with a hearing aid or with a cochlear implant. So that's how the information that I'm gathering will help the hearing aid companies hopefully to improve in the next iterations. I'm not the only one doing that research either. There's a lot of people doing that, but that's how it hopefully will help.
Dr. Heller, your research combines hearing and vision. Can you explain how our brain reconciles conflicting information when what we see doesn't match what we hear and what this reveal about sensory hierarchy?
Okay, so yeah, this is really interesting because um, vision and hearing have very different specialties. Vision is really specialized for spatial, and it's specialized for, localizing objects. It's very object centered. Hearing has a different purpose, and it's got a lot of temporal resolution, whereas vision has that spatial resolution. It's got great temporal resolution. Spatial resolution is not as good as visual. It's still reasonable, but and so when you have competing information, it makes sense that if it's visual spatial information, that's maybe going to dominate over the location that you get from your hearing. And so there are examples, many examples like that, where if you see somebody, say a ventriloquist, making a dummy head move and it's right there, and you hear speech coming from the dummy head and you're going to visually follow that, it seems, and the ventriloquist doesn't move their mouth that much, so the thing that's moving and the sound you're hearing, you're going to feel like you're localizing the sound as coming from that dummy head, even though all your auditory cues say, no, 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 it's coming from the ventriloquist, because the spatial resolution is going to dominate. The other way around, though, for time, there are certain cases where you may see, so that's a dummy head. That's not my research. That's just a real world example. But so in my research, I tried to look for cases where auditory information sort of had a benefit over visual. Some of it's temporal, like maybe brief flashes. Other people have done work on that. Like if so, there's brief flashes and you're counting them, like you'll have a temporal resolution influence on how many flashes you think you see. In the study that I did, you were able to visually influence like the path that you saw a ball take that you were watching in space based on the acoustic information about surface contact. And that's because vision doesn't really tell you about surface contact. Early attempts to make beautiful visual graphics, you would see a ball on a table and it looked like the ball was floating above the table no matter what they did. So early computer graphics was really plagued by this problem, and they had to realize that they had to put in shadows and things to really indicate that the ball was on the table. But even so, the best cue for surface contact is that rolling sound if you're moving along, rolling or scraping. So we added that, and that really made a difference in the path that they saw a ball taking when we set it up with a whole study to differentiate those things. So visually, people reported seeing something that was dictated by hearing. So in other words, it isn't that there's a sensory hierarchy overall. It's not like vision wins all the time. They each have their specialties that can influence the other.
Professor, what specific gaps exist between how machine learning systems classify sounds and how humans naturally categorize them? And what human perceptual principles should AI developers prioritize?
Yeah. It- the way that machine learning systems classify sounds, if they've been trained to classify sounds based on human definitions of what classification is, then it's kind of a different question from if you just ask them to classify sounds like on their own, right? So if we just stick to the domain of, well, humans hear things like animal sounds, nature sounds, tool sounds, we classify it that way. Can we train a machine learning system to classify it the same way that we do? Okay, so many machine learning domains are actually like this. They start from the human and then they try to learn it. And so if you take that domain, then the machines are going to make some mistakes. People also make some mistakes. People are not perfect at identifying sounds. Sounds are really telling you about an event that happened in the world, that energy was put into something to make it vibrate or move in some way. Okay, it's not designed to tell you exactly what the object is most of the time, right? It'll tell you like what the action was and the interactions between the surfaces, but not that. So when people make mistakes, they'll tend to make a mistake about like, oh, I don't know if that was a cup or a book that just fell on the floor. I'm not really sure, right? But I know something fell on the floor. So they'll kind of have partial information. And so when I looked at what kinds of mistakes people made in identifying sounds, identifying the sources of sounds, I tried to map that onto the kinds of mistakes that were being made by machine learning classification systems as well. And they were nicely predictive. The similarities in those properties were nicely predictive in some cases. And then it was interesting, of course, it's always the cases where it's not. And there are a few cases where it's not, it doesn't align because the machine learning systems are using completely different features, a completely different structure than people. You'd expect there to be some differences. So there are some gaps there, and it's interesting because in one situation we were able to take the information that humans had about what causes they thought they were when they heard sounds and improve the machine classification a little bit. We're talking in machine learning world, it's a couple percent is a help. And this was several years back, but we were able to use some human information about sort of the causal properties of the things that created the sounds, and help a machine, an automatic classification system. So because there's that little gap, as you mentioned. And another thing I did was look at a machine learning. I was part of a project that was looking at a machine learning system that was trying to tell real from fake sounds. And it did quite well in the environmental sounds we were looking at, and it did quite well, but it made some mistakes. And so we gave those mistakes to people to see if people were more sensitive in some ways. And there's two ways that a machine can make a mistake. It can hear a fake sound and then say it's real, or hear a real sound and say it's fake. And so in one class of sounds, people were no more sensitive than the machines. But in another class, people had a little sensitivity, like maybe 70% of the time, where a chance would be 50% of the time, they actually realized it was a real sound when the system thought it was fake. And interestingly, going back to the echoes, one of the examples of something that people could tell was real, but the machine learning system thought was fake, was something that was in an echoey bathroom. And so that sounded kind of like distortion to a system. But for humans who've been in an echoey bathroom, that was a familiar sort of an echo pattern. We said, oh no, that's probably actually a real cough in a bathroom or something. So that's my answer to your question.
Professor, how does exposure to unwanted sounds such as noise pollution affect our ability to process important auditory information? And what preventive strategies does your research suggest? How does exposure to misophonia triggers affect people with misophonia? And what does your research reveal about it?
Yeah, thanks for the question. So there's two parts to it. One is unwanted sound, such as noise pollution. I've been involved in a research project looking specifically at noise levels around a school and a hospital. And so in the case of a school, you can ask the students, does the noise ever interfere with your ability to hear the teacher or do your work? And so I and many other people are looking at how annoyance and stress that are caused by noise pollution can really interfere with something like learning, or in the hospital, something like rest that's needed. And so the preventive strategies, I mean, the best thing is to reduce the noise at the source. So quieter, in this case, maybe if it's traffic noise, well, there's ways to quiet traffic noise, technological ones, but I'm not going to get into all of that, right? But that's an option. That's the best one. But then if you're in a building, then there are acoustic engineers that are very good at, preventing sound from getting inside. But often the acoustic engineers are interviewed at the end of the building design or something, and it's just not central to it. So another way that this could be improved is by having that acoustic isolation in the design of the building and the rooms in the first place. So that would be an important preventive strategy. Last resort, of course, is giving people hearing protection if it's that loud. But often noise pollution that's not loud enough to need hearing protection is still a significant strain on people's cognitive abilities and emotional well-being as well, and stress levels. So therefore health impacts. Okay, now for the question about misophonia, that's a case where the sounds are also unwanted, but not for everyone. So there's a certain smaller percent of people that find certain kinds of everyday sounds extremely unpleasant, unbearably unpleasant. And people who have misophonia, they will find certain kinds of sounds, like the sound of chewing, for example, is a very big trigger for a misophonic reaction. Other things might be like typing noises or crinkling plastic. So these would be sounds that many people would just do and make and not think about it and not care. But the people who are suffering from it, they're in agony the whole time it's happening. So one of the preventive strategies there is education, that most people aren't even aware. Even if they have misophonia, many people don't know they have it. They don't know it's a thing. They don't know it has a word. So education that it exists, so that the people who have it are aware and can get resources, but also for the people who don't have it, to have some understanding that you might not bother you to open that candy wrapper in the middle of the movie, but like there's someone else that's really, really distracting and making it hard for them to enjoy the movie. They may feel that they have to leave the theater for a ticket they paid for. So, and obviously in tests and things, there should be work towards, getting accommodations for students who are very disturbed by those kinds of sounds. So those would be, very practical solutions to it. My research reveals, because I'm a psychologist looking at, memory recognition, things like that, my research really reveals that the source of the sound is really what determines the majority of how upsetting those misophonic triggers are. So if people are able to reinterpret the source of the sound as being from some other source that's not one of their triggers, then the source is not as unpleasant. It won't necessarily make it into a pleasant sound, but in some cases it actually can. So for example, if you see a campfire burning and you hear the sound of crackling and you think it's a crackling campfire, you might think it's pleasant. But then if you realize it was actually made from someone crinkling some plastic, then if you have misophonia, you'll find that sound unpleasant. So my research was really investigating what are ways we can help people if they are trying to find alternative ways to think about the sounds and to perceive the sounds. And therapy, for example, we looked at whether words could help, images, pretty paintings, movies, things like that. And so that's there's the research, the very basic research is there for clinicians now to hopefully apply.
Professor, how do we mentally organize thousands of different sounds into meaningful categories? And which brain regions are recruited during sound perception?
So a really, really quick answer to that would be so many brain regions are recruited during sound perception. It's not just the auditory cortex, but that is the place in the brain, the cortex, is where we're doing most of our what we would think of as higher level processing and thinking about sounds and cognition. The cortex is where most of that happens. The auditory cortex is where auditory information first enters the cortex. And that spreads from there to regions that deal with attention, emotion, you know, actions that we're going to make, you know, memories we have about the last time we heard the song. So it stretches, like the whole brain is involved in our interpretations of sounds. So that's my really quick answer to your question. But um, let's see. But in terms of the research that I've been doing, looking at like the different kinds of properties that are involved in detailed thinking about sounds, like what kinds of actions made the sound or what kinds of materials. I've done some work there with fMRI, looking at the specific regions that are more active when you're listening to one kind of thing or the other. And in that case, we do have strong involvement of parietal lobe. And also, interestingly, when we're thinking about material, it looked like there's some occipital lobe, which is usually associated with vision, suggesting that you're having to do some kind of multimodal integration about certain things. So that is my answer.
Professor, your multimodal experiments examine how sound affects the gestures we make. Why do humans instinctively connect gestures to sounds? And does this gesture sound connect influence how we perceive audio?
Yes. So the thing is that a sound doesn't occur unless an action occurred in some way. Energy was put into a system some way, usually in our world, an action, right? Even if it's an action like wind, you know, moving water so that there's waves, it's some kind of an action, physical action. And so it makes sense that humans, when they hear a sound, are trying to figure out what action occurred, right? So they're tightly linked in our cognitive and memory um, systems. But another way in which it's tightly linked is that when we make actions, they do make characteristic sounds. And we know that musicians know this and refine their actions with exquisite precision to get exactly the sound they want, right? So there's a tight linkage there. And so it affects how we perceive audio too, which is a study that I did, a couple of studies where I said, well, if we have this tight linkage because we make an action, it makes a sound, what if I hear the sound first when I'm preparing to make the action? And so, for example, if I heard the sound of a tap and I was preparing to make a tap sound, like would that make it easier for me to make a tap? Or vice versa, if I heard the sound of a scrape, but I was preparing to make a tap, would that kind of interfere because I'm hearing something made by a different gesture? And that is what we found. So that was sort of just a way of probing just slight differences in reaction times and accuracy to show this tight linkage and which sounds are connected to which gestures.
Professor, navigation aids for visually impaired individuals require sophisticated sound interpretation. What might be the biggest technical and perceptual challenges in translating human auditory navigation skills into reliable assistive technology?
Um, so if we're focusing on navigation skills using echoes, like what we talked about before, then I would say that the biggest challenge is that if you just give realistic echoes to humans who haven't trained, just maybe a sighted adult or maybe maybe a sighted adult who's going blind and now they want to pick up a new skill, something like that. And you just give them realistic echoes. You can try it yourself. You can walk up to a wall, close your eyes, and make a click with your mouth, and see if you can hear that there's a wall in front of you. Versus turn around to the open space and make a click and be like, oh, do those sound different? It's very, very difficult. So the technology needs to bring people along. It needs to make it easier at first and then gradually make it harder and harder. If you think about when you play a game, and you're picking up skills like a video game or something, that you level up, right, as you get better. That's the type of approach that needs to be taken, I think, in the technology, to make maybe the time delays a little bit longer than they would be realistically, or the echoes a little bit louder than they realistically would be. That's my suggestion.
Professor, I would like to conclude this episode with one last question. As virtual and augmented reality become more prevalent, how should immersive audio environments be designed to align with human perceptual capabilities rather than overwhelming or confusing users?
Thanks. Yeah, there's a whole world of research being done now with virtual reality and augmented reality. There are many great applications for it. But it is important that see, you can do anything you want in virtual reality, right? So you can make things misalign, and that's interesting for some studies, and maybe for some emotional impact or something. But if you're talking about something like wanting to help surgeon learn a technique or something, you're going to want to have those cues align as closely as possible to our perceptual system. And that's where understanding it is really important. So we need to port our understanding of 100 years of psychology research and perception research without VR, port it into VR and ask some of the questions there that we have to ask, such as that we didn't have to ask before, but we can use the knowledge we have. So we know how we 3D localize sounds from many studies in the real world. We can port that information into a VR system to give good realistic sound localization. But there are challenges with it sometimes. A lot of times the sound doesn't sound like it's outside of your head. It sounds really close to you. And so people have been adding in acoustic cues to do that. And one study that I was involved with was looking at a question that you would never have asked before VR, which is you're looking at yourself as an avatar in games and VR a lot. And you have sometimes the option with a button to either see things from the point of view of the avatar or to see things from outside, right? And so if that visual change shifts with the push of a button, should your auditory perception also change? Because that localization then of anything you're listening to that was in front of you is now maybe to your right, when you're looking from a different point of view, right, from the side of your avatar or something. Should the sound shift or not? And these are the kinds of questions that need to be asked and addressed to make visual and auditory and all the other senses make sense and be the most productive in new applications of the exciting technology advances that we've got in VR, AR, XR.
Dr. Laurie Heller, thank you for sharing such compelling insights into the remarkable intersection of human auditory perception and cutting-edge technology. Your research reminds us that innovation doesn't always require starting from scratch. Sometimes the most powerful solutions come from listening carefully to how nature has already solved these problems. From the echoes that guide us through space to the algorithms that will shape tomorrow's assistive technologies, your work demonstrates that understanding the human ear is ultimately about understanding human connection and capability. For our listeners interested in learning more about Dr. Heller's research, auditory perception, and about the future of sound technology, we encourage you to visit Carnegie Mellon's Department of Psychology website and auditorylab.org to explore the incredible work being done at the intersection of cognition, neuroscience, and innovation. Until next time, keep listening because Dr. Heller has shown us there is far more to hear than we ever imagined. Thank you, Dr. Laurie Heller, for joining with us today.
Thank you, Deepak.